hybrid vehicle. All right. All right. Where we left off, let's see. Click on the slides to actually work them. Where we left off was with, yesterday, last class, we defined the force due to a magnetic field. On a charge that's moving, the charge has to be moving, and it has to be moving perpendicular to the field. And then, explain what happens in different cases, what happens when you have an angle between the field and the velocity. And example problems. And the idea is that you're still doing Newton's laws, you're still doing F equals ma at the end of it. So things like calculating the velocity of an object or the acceleration is still viable. You just identify the force and then use it. And then we come up with the idea of applications for the magnetic field. Velocity selector uses electric and magnetic fields, and we define what's called the Lorentz force, which is the electric force, F equals QE, plus the magnetic force, F is QdV sine theta. So if the Lorentz force is 0, if the electric force equals magnetic force for a charge, then it will continue on through a electric magnetic field. And what we suggested was a setup where the electric field was perpendicular to the velocity and to the magnetic field, such that the magnetic field would point up and the electric field would point down, for example. And so that will select velocities where your electric field is just that velocity times magnetic field. If it's too fast, the magnetic force is too large. If it's too slow, the electric force is too large. And the classroom display has went to crap. And it says, please wait, it's display cooling. So give it a moment there. I mean, this is a review. That's what I don't get is display cooling in a room that has only televisions. There's no projector, there's no reason for the display to cool. All right. So we talked about the nature of motion in these different fields. In an electric field, your charge is going to basically obey projectile motion. All right, you have an acceleration. In this case, it's due to the electric force. And that means that your motion is going to look roughly like kinematic motion. It's going to look like the stuff you saw at the beginning of 111. For the magnetic field, you don't have an acceleration. You have, well, you do. You have a circular acceleration. You don't have anything that speeds you up or slows you down. You have a turning force. You have something that's going to make you move in a circle. So you're going to have circular motion from magnetic forces. What this means is electric fields do work, right? Because they can accelerate particles. They can change the velocity, so they change the kinetic energy. Magnetic forces don't do work because they make particles move in a circle. The kinetic energy stays constant because the velocity stays constant. These forces are just perpendicular. They cause rotation. So another application for the magnetic field comes in by allowing a charge to move in a circle. And we can ask the centripetal force, how does that relate to the magnetic force? Right? They're equal. And that means you have a relationship between the size of the circle and the mass of the particle, the velocity, and the charge in the magnetic field. So one place I didn't mention this is talking about aurora, right? Is if you're very high or northern or southern latitudes, you go out at night, you see glowing in the sky. Sometimes you see it closer to here, but It's pretty rare to see it anywhere near here. All right, you have to go north, basically. And the further north you go, the more likely you are to see it. So what's going on is there's a magnetic field. The magnetic field is going to be strongest near the pole, and then pole is at the north and the south. So there are charged particles coming from the sun. These charged particles are incident upon the Earth. When they're, if they hit at the equator, they're not going to do very much. But if they hit at the poles, if they see a high magnetic field, and they will twist around that magnetic field, they will obey a circular motion, which means they see an acceleration. And one of the things you learn in very high level physics is that electrons that are accelerating are also radiating energy. They give off light. So you see a glowing effect. But what you're seeing when you see aurora is you're seeing the charged particles trapped in the magnetic field moving in circles. And if they have a component of the velocity parallel to the field, that doesn't get affected. So you see a corkscrew, a helix. But there's one portion that's going to be circular motion and one portion is going to be along the field. Anyway, the actual applications we talked about were, like particle accelerators, detecting the particles, and ultimately mass spectrometry. The idea is that you can sort out particles by their mass by giving them a constant charge and a constant velocity from, giving them, have an ion source and a potential difference. And then once they enter a magnetic field, they follow these circular tracks, but the lighter particles follow a bigger circle. Their radius is larger. And so you can calculate based on, like, you have a relationship that will tell you how fast it's going, which is the kinetic energy is equal to the potential energy, which looks like that. So that tells you here, all right, when you speed up the particles, how fast they're going, you can control that. And then the relationship of the radius of the circle to the properties of the charge, the charge, the mass, the velocity, and then the magnetic field it sees. Which means you can steer particles into certain containers. But all of this comes from the fact that these charges feel some force when they're moving through a magnetic field. So there are other charges that move through a magnetic field. This was the last thing I mentioned in the last class, is that currents are charges that are moving. Generally, they're electrostatically neutral because you have a real wire and the electrons are all paired up with the protons somewhere in the wire. So there's no net charge. But there are charges moving. The atomic nuclei are generally stationary, and the electrons are flowing through the wire. And so those electrons feel a force. And so instead of trying to count the electrons and add them all up, we convert the problem to the force on a current. And we'll give you a right-hand rule here. These slides say your thumb is the current, and your fingers are the field, and you're going to push in the direction of the force. In this case, the force is to the right of the screen. So converting that, we realize that the velocity is really a change in length over time, how far the charges move over time. So for each electron, we can put in a length divided by time for how far it moves, and then we realize charge divided by time is the current. All right, so you can see what we're doing is putting in delta T top and bottom, and then converting Q to current and V to distance. And so we have an expression for the force on a current. What does it want to do is push a wire around. You have a wire in a magnetic field, it'll be pushed around. So we'll give you an alternate right-hand rule. Your fingers are the direction of the current, so you point in the direction of the current. And so what, you curl those fingers into the field, and then your thumb represents the force. And I talked a bit about what's going on here is when we define a right-hand rule, we're using particular axes that you use in math, X, Y, and Z axes, in the orders that they're drawn here. You can draw them, right? There's 6 different ways to orient them. 3 of them are just rotations of each other, and the other 3 are rotations of each other. But the other 3 represent basically a left-handed system. You interchange, say, X and Z. And so we had to take one set, we picked the right hand, and so X, Y, and Z are laid out the way they are. And so that means if you put your current along X and your field along Y, then your force must be along Z. So any right-hand rule you come up with, as long as it's consistent, as long as it goes, thumb, finger, palm, and current, direction, force, it should be consistent. All right, anyway, example problem. Not everything you need right-hand rules. Sometimes you just need the size of the force, and then to find the acceleration. And this is telling you how a speaker works. Of course, there are a couple other types of speakers, but the generic ones, the ones that you like get with your computer, or they even the ones earbuds, things in your phone, they're generally a very small coil in a permanent magnet that's connected to a cone. So the coil is given some dimensions. All right, there's the diameter D, which goes from there to there. And it contains a number of turns of wire, and it's in a magnetic field, and we're giving it some current. All right, so you identify the field, you identify the current. There's a reason for giving the diameter. We're going to identify the length as the circumference of the coil, and so it's going to be pi times the diameter. So we want to find out what the magnetic force is on the coil, and then we want to find the acceleration. Acceleration will be easy. The acceleration is force divided by mass, and we have a mass here. So everything else, we have the current, we have the length, we have magnetic field, and so our force is going to be current times our length times the magnetic field, and everything's at right angles, so we'll have sine of 90 degrees, which is 1. And we go through and calculate. Oh, that's the other thing. The number of turns, each turn experiences a force. So instead of the coil having 1 kick, it's having 55 distinct forces on it. So there's basically, you unwind the coil, the entire piece of wire has a force on it. And so the entire length of the wire is 55 turns times pi times the diameter. And so you get the force on it, and then you get the acceleration. It seems like it should. Most of these things are really, if you can identify the problem, then it's one equation plug and shove. Identify the problem, identify what you know.
So when you're looking at that picture, How do you know that sine of 90 degrees?
All right, so let's take this one part right here. The current is into the field, into the page. We have a magnetic field up. And so those two are perpendicular. That means that the force has to be perpendicular to both things. Right? But the angle is measured. Right, so if I rotate this, so let's make the current this way, and then magnetic field is still up. This will make the force point to current, yeah. All right, so this is the angle theta, is between the current and the field. As long as that's perpendicular, like the force is automatically perpendicular to both, but they don't have to be perpendicular. That's where the sign is. But you can look at the geometry of the thing. It's circular, and the field, right, is coming from this magnet, which is circular. So the field is radially outwards. And the coil is along the surface. So it has to be, this is your circle for the current, and this is your field. At all points on the circle, the field has to be perpendicular. All right, there's some other, applications of this. There's a design for a boat motor that has basically no moving parts. The way it works is you have seawater, which is full of ions, moving through this machine, which is basically a big capacitor. And the capacitor puts a charge on the two plates. There's an electric current now because seawater is a conductor. So it flows across. And you have a magnetic field from some coils that the water is flowing through, which gives you a magnetic field up, and it pushes the current outwards. So it effectively accelerates the water through the capacitor. So it works like a jet, but uses electricity to, it's a water jet. Anyway, so a bigger application of this, and one that we kind of have to look through in some detail. We're going to look at a coil of wire. So somewhere in this diagram, it's a square box, there is a voltage source that's pushing current in a circle or in a square. All right, so you've made a square coil. And you've got a magnetic field to the right. So the trick for this is, these are reasonably easy questions. We're going to apply the first right-hand rule we learned. What is the force that's going to act on these different coils, right? So A and B, the current is this way. So the current is up in B and C, it is back in C to D, and it is down in D to A. So for section B to C, your current is going to be up. Your field is going to be to the left. That means you're going to push. I'm doing this based on my screen, not your screen.
Yeah.
Current is up. Field is to the right of the screen. So the force is inwards into the page. All right, so we do it for section A to D. All right, now the current is flowing in the opposite direction. So you figure the force should be in the opposite direction, should be out of the page. And if you do the right-hand rule, your current is down and your field is to the right of the screen. And so that means that your force is out of the page. So here you have an object that has a force on one side pushing it one way, and a force on the other side pushing it the other way. It's going to rotate it eventually. So section A and B and section C and D, you're gonna ask what the force is. That current's parallel to the field.
Is this going where when it rotates, that force is then gonna happen on the top and bottom, so it's then gonna start rotating the other way?
That's a good question. All right, so for this case, we're looking at these top and bottom chunks. Those currents are parallel to the field. They don't see a force at all. Right? So what we have here is force, and they're equal sized forces. They're just in different spots. So you're not going to have a force moving the coil. You're going to have a torque rotating. And the question is, can we figure out which way it rotates? Well, yeah, it rotates around the y-axis. It can't rotate around the x-axis because then your torque is radius times force. The radius would be 0. All right, and if it's any other place, if it's parallel to the x-axis, then you have opposite torques acting at the same distance. Opposite forces acting at the same distance. The torque is 0. But along the y direction, you have that the torques add up. All right. To check, try to do the right-hand rule for radiuses along the x-axis. Sorry, radius is measured from the y-axis, so it's parallel to the x-axis. And what you see is that you get 0 torque. If you do it from the x-axis, so that it will rotate along the y-axis, then you get that the torques are both in the same direction. All right, for right-hand rule, your radius for this here is there. That's R. And so your torque, radius, force, so your torque is up. And then we do it for the other wire, your radius is here, and your force is out. Your torque is also up. So you'll have a rotation around the y-axis. Right, remember, torque is R times F times sine of phi, and everything's perpendicular here. So sine of 90 is 1. So we have a rotation. That's what's happening in this coil. So we show a slightly different geometry. Here's our coil, and we give it a way to rotate. Right, but 1 and 2 are the 2 wires that had the force on it. And the way the current's rotating here, right, we can identify the torque that we would see, which is going to be radius times force, radius times force. It's going to be into the screen. And so your torque is into the screen. It's going to rotate this way. Right, and that's what you expect, is it has this force on it. So that torque varies because it depends on the angle that your torque is still RF sine phi. So it depends on the angle phi in the problem. So there are times when it's 0, when there is no torque. Right? So that means just a single coil of wire will just kind of oscillate. It'll rotate one way for a bit, and it will rotate the other way for a bit. Right? So that's not a whole lot useful. You see these little toys in dollar stores that kind of, like pendulums. That would be kind of the motion you would expect. It's not exactly a useful thing. And that's just what happens is a coil by itself in a magnetic field is just going to try to orient itself so that the coil is perpendicular, right? The surface, the coil cross-sectional area will be perpendicular to the field. It tries to get the field lines to go through the coil. And that makes it so that you have zero torque. Your maximum torque is in the top picture, and your minimum torque, your zero torque, is in the bottom picture. So how do we make that useful? We figure out a way to stop the current or reverse the current when it's in the zero torque position. All right, if we stop it, then it'll just keep going. It'll rotate because it has some velocity after it accelerated. And then once it's in a position where we can cut it back on, we cut it back on in the other direction and it'll feel torque again. So if we want to calculate what the torque is on this coil based on the magnetic field, well, it has to be based on the force, which is ILB, and then it has to be based on the radius, which is going to be half the diameter of the coil times sine of phi. And so, well, length times width is going to be area. So this is the area of the coil. And so that lets us identify this weird thing. So for a coil, there is what's called the magnetic moment, which is basically how easy is it to be influenced by a magnetic field. And it's based on the current in the coil and the number of turns. The more turns, the more coil you're affecting. And the area, larger coil will deal with more magnetic field lines. So this seems like a sort of a superfluous thing, is we don't really need to define magnetic moment, except when we get down to atomic particles, we'll find that basically any charged particle has a magnetic moment. It acts like a small loop of current. All right, so this is a concept that extends further beyond coils we can build in the lab. All right, so we can determine for a given set of coils what the torque provided is. All right, so we have an area, we have a number of loops A, N, we have a current I, and we have a field B. All right, so the magnetic moment is part A, do a bunch of calculating, and it's always going to be in units of current times area. And then our torque, remember torque had units of newtons times meters, which is not energy, right? Because there's some hidden like angle in here that's weird. But what we end up with is we have a torque that's non-zero. Now, the purpose of this is that if we can get a coil turning, that's a motor. We can do useful work with it. We just got to get the coil turning and make it turn something else so we can turn other things like automobile wheels or CDs. So what I was talking about is, if we look at this diagram that we have here, you notice that there's brushes and half rings. There's movable connections. There's a way for the current to be on and the coil to still rotate. So this coil rotates. When it turns 90 degrees, the gap in here will align with the brushes and the current turns off. Then the coil, so let's put a positive on one side and a negative on the other. So current will always flow from the left side of the screen to the right side. But as it goes through the coil, well, it goes through the first brush, the left brush, but it doesn't matter, which half ring touches it. So when the current's flowing, it's always going to go toward the north pole of the magnet. So it's always going to feel the same force on that wire that's near that magnet.
The brushes are connected to the wires and the rings are connected to the
Coil.
rotating.
Yeah.
Okay.
This is how a brush motor works. So to be clear, there are other forms of motor. There's what's called brushless motors. And what they do is instead of having a permanent magnet, they have a set of coils. And the field in the set of coils changes as the rotating coil rotates. Right, you have some switching going on to cause it to switch as the coil rotates. All right, so there are other forms of motors, but the simplest way is you have brushes and you make it turn off and then turn on in the other direction through the rotating coil. So it's a trick to make the torque always be in the same directions. All right, so here's a slightly more better done drawing is I'm getting hair in my mouth. I'm probably gonna have to shave someday. Excuse me. So, you know, you hook a battery up to this. When it gets to one orientation, the current will always flow towards the north pole, then through the coil, and then from the south pole back to the brushes. And then when it rotates around to that point where there would be no torque, the current cuts off. And that allows the coil to coast. And once the current cuts back on, the side that would be the south pole wire has now rotated around to the north pole. And so you end up basically, the coil always has the same orientation when the current flows. All right. That's basically where I want to stop today. I mentioned about brushless motors. And I talked about coils and magnetic fields. The idea is going to be that current can cause a magnetic field. And so we're going to get into all the different ways of causing a magnetic field with a current. And then relating those to, right, one current can influence another current. So how do moving charged particles interact through magnetic fields, as well as electric fields if there's a net charge. But yeah, we got done early. This is all I wanted to cover. So if you have homework questions, now would be the time to do homework questions.
Did you end up wanting to change which questions were on the homework?
I haven't, and since it's kind of late to do it, but I mean, if people don't get done with it, I'm not going to worry too much about it.
Yeah, that's all right. I just wanted to know because I already did it, and I just wanted if I could go back and
No,
do questions.
I was not going to add any questions. I was going to take them out.
Gotcha.
So since it's late, I'm just going to let it be. And if people don't get done with it, then I'll just make it optional.
Sounds like a plan.
All right. Well, y'all have a good day.
You too. And it's Thursday. I'll see you on Monday.